their we will focus on their limitations. At the same time, I will stop this presentation in a shorter period, and we will move over to a hands-on session where I can share you some of the models and platforms that I use and I am familiar with. That might not be a complete set because you people also might know different models and platforms. Um, so, the in a nutshell, the idea is to share knowledge among ourselves so that we can tackle together these kind of emerging technologies and get a sense of what to use and what not to use, or what to do and what to expect and what to focus in the future, etc. AI, as you know, is actually a term, an umbrella term, I would say, to define a lot of involved technologies, especially machine learning, robotics, and NLP, deep learning, and a lot of things are involved. And some of them are interrelated. Some of them are subfields and branches, and under which several technologies emerged. And the world now think that AI is very powerful and even capable of replacing human uh, productivity and competence and work readiness uh, and creativity. But in reality, if you look closer about the adoption of AI in corporate world and other areas, this cartoon tells the story. Nobody is actually confident enough to di- diver, um, diverse their know-how, like especially their business knowledge, traditional practices, core and crucial data with any of the AI models, because AI models, as we know, are not there yet. That means they don't have the uh, trust and reliability to entrust all the uh, traditional, means our own intellectual property rights or business secrets to a model. So so far so good, but these systems have to evolve in future to be more reliable and trustable. Then whenever I talk about AI to people in workshops and sessions and interactions, seminars, and all these days, one of the questions that I get, a prominent question that I get is this: which AI model is the best? So this slide is meant for that, and it actually tells you a story about a person. Machine learning is a joke. Machine learning algorithm walks into a bar, and the bartender asks, "What will you have?" And the algorithm says, "What's everyone else is having?" So in today's algorithmic culture, the right choice is not always the right one, but we all look for what others are choosing or others are adopting, others are using or doing. So that kind of a situation is here. And the answer to the question is that there is no single AI model that can do everything that is satisfactory for you. For me, I use a variety of models, and depending upon the specific task that I have, I use one model or the other. And I don't trust any of these models, or I don't entrust any of these models with all my tasks, but I take them case by case, situation by situation, and use them appropriately. Most of the models I use are for free. Some of the models are paid. Some are on offer, etc. So that means you all need to have a look at the models and ask them or use them to get whatever is appropriate for you. So that is the main thing to remember. Now, looking at the evolution of AI models. So AI, as you know, was born almost at the same time when digital computing technology was born in the 1930s, especially with the work of Alan Turing and others. And machine learning model of a neuron was built in 1943 as a research area, and therefore AI is not a new technology. But as you know, the technology did not evolve until the 2010s, where we had enough computing power, data to train, and also better algorithms that can give realistic answers. So whenever I ask my students about how old AI is, according to them, mostly I get the answer 4 to 5 years. And that is because only in by 2020s that AI has reached the level where ordinary humans, people without coding or algorithmic or mathematical or logical skills, can talk to AI in their own language and get responses in their own languages. So that means AI has become democratized. It has become layman's tool only in the 2020s. But that actually is not exactly true, because people were using AI without much knowledge, but they couldn't talk to AI, get reliable things. And in 2025, we are at the end of 2025. This AI revolution, that is generative AI, happened since 2020 or 2022 in the public space. But in 3 years, it has reached immense potential, or it has shown immense potential. And today we have what is called multimodal AI, where you can input or give data or ask questions without even being using a language. You can simply cut and paste. If you can give screenshots, upload images, videos, etc. Even take data from any sensors, etc. So we are in the era of edge AI. Then we are living in the era of IoTs, and multiple sensor inputs are read by AI models, etc. So this is the era of multimodal agentic AI, and things like that. So to summarize, to sum up all the things that I have been talking, we today have large data sets to train AI, especially crucial for machine learning, and huge computational power, and plenty of open source software, and innovative deep learning models, etc., that makes computation really possible. So these things, I think you will know more about in the next session by Dr. Mithun. Here we use basically 3 things: linear algebra for computation, calculus for optimization or error correction, etc., and probability and statistics for prediction. So that is what make large language models and other AI models mostly possible. And important breakthroughs were the 1986 backpropagation work, for which the Physics Nobel Prize was awarded last year. Then in 2017, the transformer model was published by Google engineers, and that made large language models a possibility, or the self-attention mechanism became a reality that computes these things. And also today we have diffusion models and things like that. So I usually try to compartmentalize AI into 2 areas, where before 2020 we had symbolic AI using mostly mathematical models and statistical models, where intelligence was considered to be a problem of knowledge. But today we have, with immense data and computing powers, you simply can feed data, and computers will learn from data and generate patterns. And so intelligence has become primarily a problem of data. And this is the brain of a machine learning, deep learning, or sorry, large language model. Tens of thousands of GPUs or TPUs are actually used to process the text input or any other source of inputs, and calculate models such as transformer or compute, or they make use of what is called a self-attention mechanism, etc. So any sort of such a language model these days require huge amounts of compute power. So that makes it impossible for ordinary teams or groups or individuals to make any such models. We have to rely on the big companies for that. But most of the hype is about generative AI, but discriminative AI or the traditional classification prediction systems actually are the 70 to 80% of the ecosystem. They actually make our life easier without even announcing in public. All technologies that are blended together in our devices like mobile phones, computers, laptops, tablets, even machines at home with AI technology, whether it is a camera or a car, or even nowadays vacuum cleaners, washing machines, and even air conditioners, all are fitted with some chips that can compute some kind of AI algorithm. So these things are actually there, and these are the majority of AI. But we mostly talk about the hype, where AI can do everything. AI can create something, images, videos, etc., etc. But those things are sometimes on the boundary of what is harmful and what is not harmful. And also they are evolving technologies, so we cannot actually trust them completely for our work. So the next part of my discussion, this is something from engineering, where they say that high level reasoning requires relatively little computation. Like for example, if you want to calculate solve a mathematical problem, say like calculus or statistical problem, which is not easy for humans, computers actually require not much computational power. They can do it very quickly. But the lower level sensory motor skills, like say for example, you can learn driving in a day, or say for example a few days. Statistics shows that you can train a human, like a kid of 16 or 17 years old, to learn driving in 20 hours. Or you can ask a kid of 10 years old to clean table or wash dishes, etc. So those things, even though without training, humans can easily adapt and learn. But if you want to train a robot or a car to autonomously work doing any of these tasks, it is very difficult. So this is the era of such a contradiction or a paradox, where we don't actually cannot trust all AI, everything to AI models, because they have this inherent limitations. Now, coming to the natural language processing capabilities of LLMs, you all know that generative AI is the technology that uh, brings together LLMs, and they have huge foundation models or base models that are built by huge models.
Dear participants, please mute your mic. Sadhana, please mute your mic. Sorry,
Okay.
sir.
Yeah, fine. So generative AI is the thing that we talk about much for these models, and they are actually trained with data, actually textual or visual or whatever data that you can convert into numbers and embed into vectors, and they can be fed into these models. They will learn using deep learning artificial neural networks, and once they learn sufficiently, they can generate new content. So that is the idea. And these are generative models. They use deep learning networks to create text, synthetic image generation, translation, question answering, etc., etc. A lot of things that you are familiar with. But the problem with this particular generative AI or large language models is that most of them are using what is called conditional probability for the prediction. Conditional probability is coming mostly from what is called Bayes theorem. Bayes theorem is something that calculates the possibility of something based on the premise. That means whatever is given, it will calculate the probability of something based on that given information. For example, when if you ask an LLM to fill out this, the boy went to the dash, then it will compute the probability distribution of next word or subword or token, and it will give you the response that has the highest probability. That doesn't mean that that is the correct answer, and also it doesn't mean that other choices are wrong. So whatever appropriate is picked by the model based on the context, and the highest probability is chosen. So this is something that you should remember whenever you use AI models for your work, whether it is teaching, learning, research, etc. Coming to the strengths and limitations of LLMs, this sums it up. LLMs can understand different human languages. It has the ability to go from one to the other, or mix the languages, etc. are possible. And also it can understand any knowledge system or domain or subject area that is known to humans, because latest language models are trained with trillions of tokens. That implies all human knowledge is converted into computable format and trained. These machines are, or models are trained with such data. So that means all available human knowledge is used for training AI models. And so therefore they probably know almost everything that humans can create. At the same time, inherently, when you understand, I hope you had some sessions on machine learning. In machine learning, you use data for training, and actually this algorithms do is that they create some sort of a mathematical or statistical model based on this data, which actually connects between the variables or parameters inside data. So ultimately they have some sort of a connection between input and output with weights and coefficients and parameters. So whatever you do, you cannot actually avoid the errors present in the model. So if it is a realistic model, error will be always there. So these errors will always give rise to future issues. Like whenever AI gives you a response, it could go to psychophancy. That means it can say whatever it wants. And there can be serious reasoning gaps. So when you ask questions about areas where AI is not trained very much, or AI lacks exposure or expertise, or it doesn't understand the context, it will give you answers with serious reasoning gaps. That means it may not reflect with the reality. For example, if you ask it to write a Malayalam poem, you can see that it will write Malayalam poem, but there will be no sense at all, because it may not understand the language properly. The grammar and other rules and the subtleties will not be known to the model. So that actually creates a lot of issues in the answer. So this can be understood only by a trained human. Therefore, we used to say that in using AI, the domain expertise of the human user is also important. If you don't have the sufficient expertise to evaluate the response of the AI model, there is no use at all. So that is about the reasoning gap. Now, hallucination comes inherently from the AI model construction because of the mathematical uncertainties and limitations, or the errors inherently present in the model. Hallucinations will be there for sure. So you cannot avoid them. So to minimize hallucination, what you can do is you can train the model with sufficiently good raw data of yours, instruct AI to understand the context very clearly. Then you can ask the situation or create something. AI actually knows mathematics, coding, logic, philosophy, science, and a lot of things very clearly, up to PhD or higher levels. At the same time, it lacks a lot of cognitive abilities that humans have. It cannot have a clear thought or conscious process like humans do. So therefore, it cannot actually create something new out of whatever you give. It can remix or it can recreate something that is already known to it. So therefore, if you want to use AI as a scientist or a PhD scholar who can create something new, that knowledge that never existed, you will be mistaken. So you cannot do that, because AI has that much of a limitation. So it can just interpolate and extrapolate about it. And when it comes to the large language models, mostly these models work like this. When you ask something in words, the input is converted into tokens, that is subwords. The tokens are embedded into vectors. These vectors are computed with or compared and correlated and calculated with the training data, and the responses are generated based on the probabilistic values that the words picked by the models or suggested by the models. Then the output is given in your own language after this computation. It actually is a huge resource crunchy or resource heavy computation. Therefore, it is not easy for a company to give free service for using their AI models. And if you as we started the discussion by saying that there is no perfect model that you can trust completely, and there are limitations to all models. So if you want to have a better response from all the models and compare the response from all the models and choose an appropriate model, there are now mixture of experts models available now. A router will, or a software layer will divert your responses to different models or experts or agents, then retrieve their responses and select the top k value response. Then, or they can give you a weighted combination of the responses and give you the output. So such practices are there. And since foundational models are generic models, people are also building what is called a small language models, where you can build small models that can be deployed in your workstation, even mobile phone, and can be used for a specific application. So these kind of models are the current trend. For example, you can download open source models for free, install them in your computer, and run them for fine tune them using your custom data and deploy it for say your particular application. For example, suppose you want to read all the research papers coming up in, say, for example, deep learning, published online in almost all the general journals, also archives and other platforms. So whatever people publish about deep learning, it can be specific. Like, for example, you are working on a specific area of a deep learning. Then when people are publishing papers online, you may not get time for going and reading everything. So what you can do is you can build a language model that will get API calls or explore data from all these online resources, read them, summarize them, and give to you as a daily summary. So when you wake up, the summary will be ready based on the all data that was published yesterday. Another example could be like, say, you want to invest in the stock market, and based on the available trading data yesterday and all the financial, socio-political, and other parameters that may influence the stock market decisions, you can create a model that will run in your computer. It will source all the relevant data from online resources. Sometimes you may require API access and other paywalls to access data. So whatever be, you get data, and this model can run successive machine learning models and algorithms, so that you get a summary of what to do tomorrow. So that could be your training strategy for the next day. So this is how you build a small language models suitable for specific purposes. These days, you can also use AI agents for such applications. AI agents are tools that can perform such tasks using a foundational model or some kind of a small language model. So, and also when it comes to using large language models, you should also know how to ask questions. So these models are built with deep logic and reasoning. So chain of thought prompting, that means step-by-step reasoning and detailed requirements are asked or given to the AI model, it will give good responses. And this is how LLMs have evolved. We had large language models as standalone LLMs earlier, like GPT-4, BERT, or Grok, Claude. All these foundational models, base models are there. Then they started integrating tools, various tools with these models. For example, I mentioned about small language models and specific applications. Suppose you want to work on reading PDFs, or generating images, or creating slides. So these are specific applications. So if you want to fine tune your large language model, people have built specific tools or applications or layers on top of this. They will customize or fine tune your requirement and give you better responses. So this is how LLMs improved, and you can they are available in our base models these days. I will show you some examples during the demo. Then there came what is called MCP, or Model Context Protocol from Anthropic, which actually helped AI models or agents to talk to each other. So that when you deploy an AI agent, it can talk over to other models or APIs online without much issues. Just like computers talk to each other using TCP/IP, these models talk to each other using MCPs. So this is the evolution, and today we are living in the era of multi-agentic systems, mixture of experts, and agentic AI, things like that. So that is how things are today. And you should also remember that we are now witnessing a time where the content created online, that means all the articles you read, all the news you read or hear, etc. So those are actually created more by AI than humans. That means over the internet, human created content has now given way to AI content. And also more internet searches are being done by AI agents than humans. So people don't actually now use Google and other search engines or platforms to ask questions. They simply ask AI models, and AI models go there and ask, do the search using agents. So this is the time. So content creation, exploration, search, generation, everything is mostly by AI. So will it be replacing humans in the near future is the question now. And these are some of the LLM-based models, foundation models I talked to you about. I don't know whether you have heard about models like Falcon, Turing Energy, Lambda, Palm, etc. So plenty of them are there. I will show you a platform where you can see all the models later. GPT-5 is there. So this slide is a little bit older. I took a picture from somewhere. Latest models are there. Then there are open source models like Kimi. Kimi 2 is a very advanced open source AI model from China. What actually is the difference between an open source and a closed source model? Open source models have a few features, like for example, we can do a crude comparison, like if you are using Microsoft Windows and Linux, one is proprietary, closed source. You can use them, but much of the source code and the working of the OS is not revealed to you. That they are the trade secrets or proprietary knowledge of Microsoft. Whereas in Linux, you can download the OS, you can build your own OS, you can modify anything, you can use, reuse, even make money out of it, no problem. Just like that, in open source LLMs, once the learning process is over, that means when the machine learning model learns, it will create a relation between the input and output, and it will have some sort of mathematical or statistical model with the connection between input parameters and the weights to output will be there. So proprietary companies, closed or open closed source models won't reveal that particular learning data, learning process, and the learn to model weights and all. But open source models will give you the model weights, provide information about the training data, and the model code is also available so that you can download them, You can fine tune them, you can modify the weights, etc. if you have the technical know-how. So they will allow you to use it as yours. So such models are a little bit safer because you can download and deploy it in your computer and use them without internet also. So that makes your data safe. Whereas proprietary LLMs are very powerful because they are made by biggies, and they have well documented APIs, management infrastructure, safety protocols, and they give you regular updates, etc. You can have the comparison between Linux and Microsoft here, or Apple OS here. But the cost of using is high. You have to depend the user for everything. Transparency is less. You don't know whether your data is being used for future training and business for the company. So those things are there. So coming to the last part of my presentation, these are some of the multimodal good AI models that we are going to compare now. Um, Google Gemini is there. If you have a Geo account, they will give it, the Geo gives Gemini Pro for 18 months for free. ChatGPT Go is also free for 1 year. I use ChatGPT for my daily activities, Gemini for creating images, and since it integrates with the Google Apps, Workspace, Docs, Slides, Calendar, Mail, etc., I use it as my productivity tool that connects with all my applications. Whereas for my academic research and prompting and all the serious work, I use Anthropic Claude, and that is the model that I pay for use. Whereas Perplexity is free for Airtel customers. I use all other models. ChatGPT Go is free for 1 year, and other models I regularly use for free. And if you want realistic comparisons of models and other things for social media analysis, fact checking and all, Grok from Microsoft is a good model. Meta is there in your WhatsApp and Facebook and all. DeepSeek, Quen, Mistral, Kimi, all these are open source models. Mistral is a French model, but others are Chinese. So I think Kimi 2 is the latest best open source model, whereas Gemini 3 Pro, Anthropic Claude 4.5, Opus are the latest models with very advanced significant benchmarks these days. But whenever one model gets published, the other company comes up with a even better model in a couple of weeks. Now ChatGPT has a code red situation because Gemini has doubled their customers from something like 400 million to 800 million over 3 months. They have a huge corporate client, and Anthropic Claude is the favorite app of corporate businesses because of their transparency and quality. So that makes ChatGPT at a disadvantage. So they are working on the next model to overcome this difficulty. So this is a rat race or a high competition that is happening there. So this is a comparison of all the possibilities of AI models. Like ChatGPT is very good for brainstorming, idea expansion, coding, debugging, etc. for your daily creative coding and everyday productivity workflows. Grok is good for real-time trends, social media analysis, pop culture, candid insights, comic, and all those things. It also has a powerful video, audio, and image generation tools. But Gemini is very good for integrating with your workspace and give real-time data access. Gemini also has very good image generation in Nano Banana and also video generation in Veo. Claude is good for deep reading, comprehension, ethical reasoning, academic and research purposes. Perplexity is something that you can use for, say, search engine, fact checking, summarization of knowledge. It also gives you daily updates about whatever is happening in the world. So that means you can use all this, but there is no single model that works for everyone. And in research area, people are again using the idea of generative AI to create more 3D models of amino acids, um, proteins, genome structure, etc., etc. So that means if you are inclined to do any research in these particular areas, there are very powerful models out there, which are not actually language models, but they use the generative AI principles of language models for scientific prediction and analysis. Now, the last part, that is the limitations. One limitation for large language models is depicted in this particular slide, where you call it a multi-hop reasoning problem. So imagine about these big questions being asked. Which movies directed by people born before 1955 won Oscars after 1995? So you just think about it for a few seconds, where I will drink some water. Okay, I'm back. So if you ask a human this question, for example, if we are asked this question, what we will do? We will do a search, Google search. We will look into Wikipedia, then IMDb and other databases. We will write down all these responses. We will compare different databases and we will find the answer. But for an AI model to answer this is not very easy, because it's called what is called it uses what's called a multi-hop reasoning problem, where it will need to have different API calls, retrieve information from multiple databases and compare them and blend them and filter them to give you the answer. So this kind of tasks, even though it looks very easy for humans, these are pretty much computationally intensive and difficult for AI. So this is one problem. Another is already I mentioned that they use conditional probability based on bias theorem. So the knowledge created by AI models is Bayesian. That means the prior is very important. Whatever known or trained to the information trained to the AI model is only what they can generate. So it cannot create something new like a human will invent or create out of blue. Spontaneous or what is it? Serendipitous inventions are not possible for AI, because it cannot think like humans. So what actually people are doing these days? AI big companies are actually hiring humans to train AI models in overcoming all the deficiencies. Like if AI fails in giving some response, they are hiring people to make those issues go away. They will modify AI responses by giving human insight. So there is a huge money being given to experts in training AI. So that means these models will be capable or capable enough to do better than humans in near future. For example, AI models can read any science paper published online and extract the information very clearly than most of the humans. For a human, you cannot read multiple papers in a day and arrive at extract information, whereas AI can process thousands of papers very quickly and extract information and process information and do whatever it wants. So I was attending one of the webinars by Nature magazine a month ago, where I saw a Chinese professor of chemistry or material science. He was presenting that they have this lab robots being used in their laboratories, as well as companies like China Energy, where these robots can they are connected with the internet. They will extract information from all the available public. They can read scientific papers published in the domain. Then they will extract those information, and if some new method or material preparation strategies has come up, they can order the chemicals and synthesize these chemicals and make things autonomously without being any human involved. So that is a kind of scary situation that we are facing at one end. On the other end, AI has a lot of limitations. And finally, AI models, these models require huge computational power. GPT-4 was trained with the 10,000 NVIDIA H100 GPUs, whereas Grok 3 was trained on 100,000. That means 1 lakh H100 models. Nowadays, Google is luring people into using their TPUs, tensor processing units. Their AI model is nowadays trained with that data. Anthropic is also shifting to that. And also Google is trying to send their data center to the space to work like International Space Station. So it is a huge business, very capital intensive, and scary situation is out there. So therefore, this actually shows one thing: there is no future without AI. That means 500 billion to $1 trillion is being invested in or pledged by a single company in AI data center and warehouse and other technology developments. So that actually means now they will not want this technology to fail. So it will be integrated into all our models, and therefore the future will be either human AI cohabitation or collaboration, or some sort of AI dominance, like all white collar jobs being taken over by AI, or many of the tasks will be automated by AI, where humans will be required only for specific high level or creative or reasoning tasks, or for blue collar jobs such as plumbing, cleaning, electrical work, etc., etc. All other middle level jobs will be done by AI, because AI is actually achieving that much of accuracy. So, so takeaways from the presentation is that AI has a powerful tool. AI has that power to be a significant potential in the future. We need thoughtful ethical implementation while adopting AI. And if you use AI, or if you are in any human expertise or domain, you need continuous learning and adaptation, because technologies are evolving that fast. So you cannot sit idle for a long time and let this technology go away. So if you have any specific doubts or clarifications regarding what I have already said, you are welcome to do that. Otherwise, I will be stop sharing these slides. Then we will go to the demonstration mode, where I will show you some of the models, the possibilities, their limitations, and I will also show you some prompts. Let me share my screen. Yeah. Are there any clarifications, questions? Okay. So I have a ChatGPT as a desktop application in my system. The latest model is 5.1. It is the flagship model. There are two possibilities. You can straight away start chatting or asking questions or interacting with it. Also, you have the scope of temporary chat. That means this is a temporary chat where it won't appear in our history. You cannot, once you close it, it will be gone. They say that they won't use your data for future training, memory, commercial purposes, etc. But they will keep it for 30 days. But you will never know. Anyway, we have to trust their statement there. It's a company. So ChatGPT 5.1. You can use research if you want further deeper Q&A session. You can also use web search, etc. So the several options are available there. So I will go back. So that is ChatGPT for you. Then I also have a Claude. So Claude is a very powerful application, Anthropic Claude. So let me open a new chat. Okay, I'm showing you some older chats. Let me close it and open. Okay, there's some issue. This is an application that I use for my teaching, research, and creative and several stuff, because it helps me to get better outputs out of these models. Then also you have a browser from ChatGPT and OpenAI, which is called Atlas. You can install it, but I was not using that for much thing. It brings you the power of a browser. At the same time, it has these AI capabilities, but I am not using it much. Perplexity also has a browser called Comet. So Comet is here. It can give you responses. You can chat with it. You can have plenty of possibilities with it. Just like using in an app, you can use Perplexity browser. So that is there. Okay, let me see. Claude is not loading properly. Okay, now it has come. So this is the chat interface of Claude. I talked to you about tools available here. Claude say it has connector. So you have plenty of connectors available. So you can see that they are meant for specific applications, like say Candid is there for research, non-profits and funders using Candid's data. So it's a platform. So if you are a non-profit NGO or a funder working on in socio-entrepreneurial areas, you can use that database for AI applications. Then AWS Marketspace and N8N. N8N is an agentic workflow platform, which you can use, crypto.com, GoDaddy, Kiwi, Snowflake, depending upon your purpose. For example, if you are a science researcher, PubMed is a publication platform. You can link it with biology. Researchers use BioRender. So when you work on something specific, you can connect the interface with that specific app connector, so that you get a better response based on those things. Otherwise, your responses could be generic. So Canva is the so that is the possibility of connectors. Then it has plenty of connectivity with your toolboxes like workspaces, Gmail, Calendar, Google Drive, etc. Extended pinging is there for deeper answers. Research is there for your query. So then Sonnet as Opus 4.5 is the most capable model from them. For everyday tasks, Sonnet 4.5. Haiku is for fast and quick answers. There are previous models also available. So these are the latest models from Claude. You can use it for learning, writing, coding, etc. At the same time, Claude Code is one of the best vibe coding application that many people use it for coding using English without much coding experience. So I have that also. That interface is also here. So this is the Claude Code interface. So you can see that it can work on that, but a specific application layer. So it has a local computing interface. That means whatever you do, it will test and exploit and implement in your local machine. Whereas you can also connect it with your GitHub and your repositories, your other platforms, etc. So it's a very powerful thing. Without any coding experience, you can create code in any particular language, test it, etc. etc. So this kind of an agentic AI mixer of expert kind of thing that you can use. One thing I use AI is to in my teaching I use AI for creating course lesson plans, custom slides, etc. So I upload syllabus, the framework, evaluation strategies, previous questions, etc. So it makes me, as you can see, So I teach fundamentals of data analytics this semester for UG students as a skill enhancement course. So I create all the course content for my lectures. Then it will generate experiments, and for my classes, I ask it to generate slides. So see what it has created for my first lecture on statistics. Let me, there it is. Okay, so this is my first lecture. The advantage is that it creates in HTML with even animations and illustrations and images. I can simply share it with my students. The advantage for HTML is that they can open it in their mobile phones using their browser. No other application is required, and it will be very frugal, and it will be very convenient for them to you open it mobile phone screen, because it will appear in the landscape. Sorry, the typical is it not visible for you? Can you see the? Okay, it is free for obviously, but I have the paid version here. But if you want small specific applications, it's free. But the problem with the free version is that the responses will be limited. That means you cannot ask many questions. The content generator will be limited. Otherwise, you have to pay. That is so. I have this this Claude. It has a free version, as well as it has just like ChatGPT. It has different layered structure for paywalls. It has pro version, it was advanced version, etc. But what I use is a pro version. So it creates slides like this. I will show you one example where it has, for one of my lectures, it has created animation. So I'll show you that. So see, so I was preparing a talk on quantum science and technology, because for a talk in a college, for where they wanted to wanted me to lecture on the quantum nature of electrons and photons in today's technology, especially in electronics and photonics. So I created a presentation based on that. Then I asked Claude to generate some animation so that I can explain the quantum nature of particles and light when the dimensions are in the nanometers or the present day dimension. So it has created this animation. You can see it actually has see, I simply gave an instruction, and it has created a dashboard with so this is where you can it actually mimics or model the random motion of electrons in a metal like say copper, where the gray fixed points are atoms or nuclei. The blue ones are the electrons moving around, colliding with each other, and also with the lattice points. So they this process, this collision actually creates the electric resistance. When you apply the electric field, you can see that the net electric field is there, and then the electrons achieve what is called a drift along with the random motion. So electrons actually doesn't flow like water in a river or a pipe. They actually drift towards the applied electric field, the direction of the current flow. So, or the opposite way, because electrons drift in the opposite direction of the current flow. But you can see that the field is actually propagating, making the current possible. Again, it mimics the band diagram there. So that is how it models. So again, it has created quantum confinement, as you can see. See, size comparison of 3 different. The animation it has created using, I think it's Node, React, or some kind of software coding it is using. The animation, I'm not sure this is Java. I haven't looked at the source code. Anyway, you will get it in HTML as a dashboard, so you can see the quantum dot where electrons confined in 5 nanometer boxes are actually stationary, so that they cannot move around, so they form standing waves. So this is a semiconductor heterojunction where gallium arsenide and aluminum gallium arsenide junction is formed. So the electrons are trapped inside in the boundary. So this is being used as a quantum version, means making LEDs or laser diodes, etc. So this is how you use AI these days for productivity. So you can ask complex tasks. You don't have to know any of these coding skills or animation skills, etc. AI will do it for you. So that is the beauty of it. So so that is about Claude. So you can have plenty of possibilities. When the first lecture is over, I can ask it to create this next slide. It will do that. So it has created the second presentation. Let me show you the. So this is how I navigate the slides. So you can see that the slides are easily navigatable with necessary. I can look at the content created. I can modify if I'm not satisfied. It will create. And one advantage of using this to create your AI means the courseware is that you will get continuity across your lectures. You can ask it to generate notes, study notes, lecture notes, and also model questions, quizzes, etc., etc. And the teaching and learning practice becomes very, very easy than before, so that you get more time in the classroom for discussing a lot of things, because content delivery is mostly done with the help of AI. Students are satisfied. You can always take them to a higher level with such technology. So this is the power of large language models these days. They are very good at understanding science, technology, mathematics, and a lot of things. They fail in understanding human-like things like literature, language, culture, and all those things where your expertise is required. And at the same time, they will also make mistakes. So that also you should know. So let us go to other models. I talked to you about say Grok, which I know you all know. So this is a Grok. Then let me open other models also. DeepSeek is there. Kimi is there. Then from Alibaba, the Chinese big data giant, we have Quen. So this is Grok. Grok is very good, but I don't have a paid subscription, so the responses will be minimal, or it will ask me to. But image generation, animation, all those things are very, very powerful with AI. So for example, yesterday I uploaded an image and asked it to create a video. So see what it has created. It will create videos with images. Sound. It will do it in a very quick time. Okay. So that is how it creates. So I uploaded a picture, and it has created two versions of it. I can choose whatever is comfortable. Then there is a DeepSeek. DeepSeek, this is the chat interface of DeepSeek. DeepSeek has a good mathematical reasoning model, because they fine-tuned the deep learning, reinforcement learning model that was successful for the OpenAI and others. And they implemented in a low resourceful computing infrastructure, and came up with a very good open source model, that is DeepSeek. Kimi is a wonderful model from China again. This is considered to be the best large language model as per benchmarks. And Kimi can create you a lot of things like data visualization, mobile application, web app, blah, 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 slides. And then you also have, if you have a paid subscription or credits, it will work as an online computer for you. You can ask it to do anything if you want. So that is then Quen, Alibaba Quen is again, so it looks almost like Gemini here. So Gemini like interface here. So it has plenty of possibilities. Quen Coder, etc. is there. So you can see there. So Quen 3 Max is a model. Quen 3 strong visual language based model. That means image processing and video processing. It has a powerful model. Quen 3 Coder is there for code generation. Dense vision language model for vision language 32 billion parameter model. So based on that, plenty of options are there for Quen also. The only issue with Chinese models is that people are worried about their data, because all these data will go to the servers of Chinese companies, where you don't actually know what they will do, etc. But the same is true for American companies also. They may use it for making money, etc. So privacy, secrecy, security, intellectual property rights, etc. are a concern. So Gemini is there. So I have a Gemini Pro subscription because of Geo subscription. Geo will give you open source. So let me open it in Chrome browser. Okay, so this is a Gemini interface. Here you can see that it has a Nano Banana image creation interface, video, write anything, learn, help me learn thing, because Google has this tool called Chat LLM. Sorry, not Chat LLM, Notebook LM. Notebook LM is a powerful RAG type training platform that helps students to learn using custom data. For example, you can upload your textbooks or your research paper, etc. It will help you to understand complex ideas easily, to study, to create videos, to create podcasts, animations, whatever you want. So those things are there. So this is so thinking thought reasoning models are there. Then tools, plenty of research model is there. Video creation, image, canvas is for slide preparation, guided learning, etc. So one advantage with all these models is that OpenAI model is the ChatGPT is integrated to Microsoft GitHub and other platforms, Microsoft Office applications. Likewise, Gemini platform is there in all Google applications, so you can your workflow, your productivity, etc. get increased with the use of these models. So Gemini, then what else? Mistral AI is a French company. So this they have LeChat, which is again a very good model. So you can use that also. So then there is another model called a GLM 4.5, which is again a very powerful Chinese model. This is by a company. This is a consortium of AI companies. I think some sort of public sector company is making this. They are actually the consortium of all Chinese provincial governments. So this is like a public sector company in China. So they have very good advanced models. So they have they have one more business in China because of the government support and public sector nature for AI applications and all those things. So you can try this. See, full stack, magic design, deep research, write code, slide generation, etc. So as I began the presentation, there is no single model that works for everyone. So you need to check all these models and find out whichever is good for your specific applications. Then you will know what to do and what all not to do. Then there are other applications built on the basis of such foundation models, like Julius AI. Julius is an online data analysis platform which helps you to analyze data without any understanding of whatever data is there. For example, plenty of data analytics work will be done by this. So for example, when I upload a CSV file, it will write the code and create the Python codes for say pandas and other data frameworks and perform everything. Then it will create analysis. See, simply uploaded a data, then it has generated very good quality images based on my data. So I can download it and use it anywhere I want. See the clarity of the visualization. So whatever you needed for data analysis, all those things can be bypassed or sidelined by using such tools. So it finds the correlation between variables in the data. You can ask anything about the data. So it's like you upload a data set, then you simply ask questions about the data sets in English. You don't need any coding skills or statistical skills or any kind of specific programming skills. You can simply ask this particular AI model and it will give you the responses. Same thing you do with ChatGPT, Claude, Gemini, etc. But there you may need a little bit more insights. Here it is, again, I am using a free version, but the responses are limited. If I want a serious make use of such applications, you need to pay. So my advice about paying for using this models is that if you are a student or a limited user, there is no need to pay. You can use free versions, and at the same time you can try exploring offers like Geo Gemini 18 months offer, or Google Go offer 1 year free for you will get the model, which actually needs 390 rupees per month. Again, Perplexity Pro is free from Airtel. So such models you can explore. But if you can generate more money, or if you are serious researcher or a professional co-programmer or someone who can make more out of such payments, then there is no problem in paying like say 2,000 per month for such an application. So that depends on your requirement. That we cannot actually predict who requires what and what level and higher things like that. So I think I have covered all the AI models that I know. Okay, I will show you the Hugging Face community platform. Hugging Face is a platform where you can create a profile. It's a community platform. All the models are available there for downloading. So you can see that. So these are all the open source free models are available there. Plenty of models like in Microsoft Voice, NVIDIA Nemotron, Alibaba Pi, Apple Starflow, etc., etc. So there is no limit at all. So you can find hundreds of AI models, and you can download them using Python or some installation code in command line or graphical installation platform. So Mistral based models are there. Depending on your computational power, you can download small models or large models. Then customize this particular model for. So for example, this Comfy model is for image generation. If you have a sketch by, say, for example, a school kid has some crayon sketch, using Comfy, you can actually convert this into real Disney-like or studio-like animation or image, cartoon character, etc. So that kind of a workflow can be created using such models. So whatever is needed for you. So for example, Quen is here. So just download it, install it in your machine. You may require a very good computing machine with a GPU card or GPU chip with sufficient video RAM and the memory, and also require some kind of technical know-how to maintain such hardware and also install and use such software. It's not simply by like downloading and clicking and installing. You need some kind of technical know-how. Sometimes you may require to hire people to do that work, but that is not free. You need to pay something. But the advantage is that you can train such models with your custom data, which is unique. That means you don't want to share with anyone, any company or any person, because that has some sort of business value for you. It can generate, for example, suppose you have some traditional Ayurvedic knowledge, which you want to use to make medicines or some kind of practice and make money for you and your family. So if you use some AI models to train on that data and make money for you, then the data will become somebody else, because there is no proprietary information. When you upload to a server, people may use it for future training, and your knowledge becomes universal. So that kind of situation you may, if you want to avoid, when you are publishing a new paper or applying for a patent or some sort of business secrets, traditional values, etc., then you need to isolate your data from the internet. So in that situations, these kind of models can be used. This is called RAG training, retrieval augmentation systems, or you can build your own agents and platforms using these kinds of software. So even though it looks fancier, these kinds of things mostly work on command line interface. That means only text will work. Even if you want to upload images, you need to code, give the code for uploading images. It will not work on a click and upload type interface. That will work for ChatGPT, Claude, etc., because they have built the interface, user interface for you, and agents for you to communicate with the foundation model and you. So the foundation model actually won't be comprehensible for human ordinary users. It works mostly on textual inputs. So therefore, you need an agent like ChatGPT or a Claude interface to interact. So I will show I will stop here by showing one of the limitations of AI here. So I have uploaded this to ChatGPT, one image where you can see dots, which are supposed to be blue dots indicates helium molecules and red indicates oxygen. I am asking it to count the number of molecules. Let us see what it does. So the problem is that it will do the calculation, but you can count the number of blues and red dots on the screen or in the image easily. I will show you the actual image. So this is the actual image. You can easily count. But when AI does it, it may find out a word. So let me show you a new Claude interface and ask one question like, it's a simple question. Is there a seahorse emoji? That is my question. Let me go back to ChatGPT. So ChatGPT has counted the number of red and blue, etc. So you can see that in compartment A, I have say 8 helium and 4 oxygen, but ChatGPT has counted this as 10 and 4. So you can see that strong. Again, in the other side, I have say blue, that is helium is 2, 4, 7, and the other is 6. Let's see, it has counted 9 and 7. So totally wrong. So this actually means it fails in understanding some small images, geometry problems, school level geometry problems, it will fail. So that is the limitation. Or even see the money that you have used for training this model is billions of dollars. Still, it cannot perform simple tasks like a human can. So that is the disadvantage here. Then see, I asked if there is a seahorse emoji. Emojis are Unicode characters. Actually, in Unicode, there is no seahorse emoji creator. So, but AI says there is a seahorse emoji. Then it tries to actually blend a horse with say some fish, and it fails. Then it says I am kidding, and then it comes with a shark image. So then again it understands that it's just mistaken. So it tries again. So then it comes with a shell. Then it ends up with a horse. See, ultimately failing miserably. So the information is wrong, but AI won't accept or admit that wrong response, that it cannot do simple tasks. So it actually tries to fool us. So this is the kind of hallucination and psychophancy that I was talking about. So in a nutshell, AI models are very powerful. See, at the same time, it can read any number of research papers published in any complex areas these days, very quickly, better than any human. At the same time, it fails in simple tasks miserably. So that is the dichotomy or paradox that AI is in today. But we cannot actually predict where it will go, because people are investing huge amounts of money in training AI models to outsmart humans and achieving human like or better consciousness or complex reasoning skills, etc. But since we don't actually know how human consciousness and activities work in reality, we cannot actually transfer that knowledge. But computationally, computers are smart enough to outsmart humans. They are very powerful, fast, quick, and reliable also. So that is why this technology has evolved so much. So that's all from my side. I'm happy to share or discuss anything if there is.
Dear participants, if you have any questions, please feel free to ask now.
Yes, I will have a look at whatever is there on the chat box. Please share the link. Claude, actually, you can simply look at. So Claude and all other applications you can install in your mobile phone and also in desktop computer, also accessible from a browser. So so that you can do. Then what else? Is there any AI to read and summarize research papers and also such papers on specific topics? So there are plenty of platforms for literature review, research summarization and things like that, called Research Rabbit, SciSpace, Synapse, Litmaps. So simply do a search for AI tools for literature review and research summarization. There are plenty of tools. Research Rabbit is something that I know. Litmaps, Connected Papers, Semantic Scholar. Like that, there are plenty of similar tools for research. So they will help you to find all the connected papers in a specific area, understand and comprehend these areas, etc. So you can ask questions to them, etc. So any other questions
from the participant side?
I haven't touched upon the technical side of this large language models and computation, etc. That I think will be covered, or interested people can simply do a search and find out.
Sir, I think no more questions from the participant side.
Yes.
So thank you so much, sir, for the very informative session, sir. Thank you for accepting our request and for handling the session. Thank you so much.
Thank you very much. Have a nice day. Bye.
Okay, sir. Thank you. So, dear participants, the next session will start at 3:30 p.m. itself. Please join.
Welcome participants to the next session on mathematics behind AI. The session is a bit theoretical in nature. We will see it in one go. The resource person for the session is Midhin A.V. Mr. Midhin A.V. is an assistant professor of computer science, currently working at Nehru Arts and Science College, Kanyanad, Kerala, where he also serves as in charge of Department of Computer Science. He holds a strong educational background, including an M.Tech in Computer and Information Science from Cochin University of Science and Technology, and B.Tech in Computer Science and Engineering from LBS College of Engineering, Kasaragod. He possesses diverse professional experience spanning both academia and industry. In the industrial sector, he worked as software analyst at Bally Technologies India Private Limited, where he focused on gaming protocol updates. Prior to that, he was a senior software engineer at In India Private Limited. His expertise covered diverse computer science subjects, including C, C++, DBMS, computer networking, etc. Welcome, sir, to the session. Thank you for accepting our invitation.
Okay, good afternoon, everyone. Thank you, Justin sir, for your warm introduction, and thank you for giving me an opportunity to take a session on this workshop. So, am I audible and am I visible to everyone?
Audible and visible.
Okay. This is okay. So the session, as we already mentioned, it is a bit theoretical in nature. The title is Mathematics Behind AI, but basically we'll be focusing only on one part. I think I'll do a recap or refreshment of what you already know about linear algebra. And I think we have only 2 hours left, so I'll try my level best to cover whatever I have prepared for today. So to understand whatever things you learned for the past 5 days, you've been going through many of the latest AI or ML or deep learning related stuff. All those things are relatively newer items or newer things, but what we'll be dealing now will be very older stuff. Like these are all mathematics, so there is nothing new in today's session. But what I'll be focusing today is how these older topics are related with this new trends that you have already learned for the past 5 days. Okay, so if you want to be an expert in machine learning, or if you want to do more research or other kind of activity in machine learning, you need to understand the mathematics behind all these steps. So basically, you need to understand these 5 areas, which I'll say. First one is of course machine. In machine learning, you should be very comfortable in linear algebra, and that will be the focus area for today's session. And apart from this, there are other areas in mathematics that you should also be familiar with, but I think we won't be able to cover those things today. And I'll just mention them what they are and how they play a role in the machine learning domain. So regarding probability, machine learning involves predictions or classifications, right? So some model will predict something, or it may be a regression or a classification or clustering or something like that. But when you predict something, there is always a level of uncertainty, right? So if you classify something as a dog or cat, there is some level of uncertainty. Or if you predict a continuous value, there is also some level of uncertainty. So to quantify the uncertainty, we need probability. So we need to know about probability and different types of distributions to understand how the data set is distributed. So for that, you need to know about probability, especially conditional probability. Okay, and then machine learning is all about data, right? You have a data set. So when you are dealing with data set, you should be knowing statistics. So you need to collect data, you need to pre-process data, all those things. For all those things, you need to know about statistics. And then we need to also visualize the data that you have collected. So you need to be familiar with the graphs and other plot visualization techniques to be good in ML domain. And finally, you need to know something about calculus, specifically multivariate calculus, which we'll be using in optimization and all. So out of these 5 topics, I think I'll be focusing on linear algebra only. Other areas I just mentioned, these are all the things you should be knowing before you get deep into the area of machine learning. And to talk about the foundations and pillars of machine learning, I can say that, as I already mentioned, linear algebra is one of the strong foundations for machine learning. Why we can say that it is the strong foundation? Because every machine learning model might require some kind of data set, most of the machine learning. Okay. So you can represent data means in machine learning, everything should be represented in numbers, right? So when you represent numerical data, you take a sample, and every sample will have a set of features. And when you write down the set of features for a sample, what you're getting is a vector. And when you stack many such vectors, you'll be getting a matrix. So So actually our data set is a matrix. So when you talk about vectors and metrics, that's linear algebra. So we can say that linear algebra is one of the strongest foundations for machine learning. And then you can see analytical geometry here. Analytical geometry means you are talking about the distances and similarity between the vectors. So for that, you need to know about analytic geometry. And then about metrics decomposition. So you have a huge data set, and then when working with huge data set, the performance will be one of the major concerns. So there should be some ways to improve the performance of machine learning models by tweaking the data set. So there are some technical metric decompositions, eigenvalue decomposition is there, singular value decomposition is there. All these things will come under metrics decomposition area. And then, as I already mentioned, probability in many machine learning model, you need to quantify uncertainty. So for that, you need to understand probability and distributions. And the need for vector calculus is for the is for finding the parameters for your ML model. So basically, in case of a linear regression, you'll have a linear model, and then you have to find the parameters for the linear model. So for that, you will be using gradient descent algorithms and also. So for this, you need to understand vector calculus. And to maximize or minimize some objective function, you should know about some of the optimization techniques. There are different kinds of optimization techniques, constrained and unconstrained optimization techniques. And so basically these areas forms the foundations for machine learning. And you can see the pillars are definitely for the machine learning. The pillars are regression, dimensionality reduction, density estimation, and classification. So all these forms the foundations and pillars, or mathematical foundations and pillars of machine learning. And how do these different areas are important to machine learning? I've taken this from one of the websites, and you can sum up like this. 35% of this will come under linear algebra, 25% for probability theory, and then 15%, around 15% for multivariate calculus, and 15% for algorithm and complexity, and then for others there will be some 10%. So I thought I'll take this 35% and try to explain. I won't be able to cover all things in this 35%, but I'll try my level best to do whatever I can. Okay, so let's focus on linear algebra. So before that, there are some fun facts, some memes I've taken from the website. So when somebody asks you what is machine learning does, even though it comes under computer science area, you can say something like this. You pour the data into this big pile of linear algebra and then collect the answers on the other side. So you have a big pile of linear algebra and you pour some data into this pile, and then you're getting an answer on the other side. So obviously the question will come, what if the answers are wrong? If they are wrong, what you can do? You can say that just stir the pile again, and then you're getting a better answer. So basically that is what gradient descent is doing. You are continuously optimizing your model so that your predictions are improving. So you're applying linear algebra again and again, and then you are getting a better result for each time. So this is what this meme says. And then how can we relate the linear algebra and machine learning? You can say that the data set, you can imagine a data set like this. A data set is basically a matrix of rows and columns. And you can say the columns are features of data and the rows are different samples. So in this particular example, there are M training samples and then N features. So if you take a column of this data set, or if you take a column of this matrix, you can say that those are different observations of a single variable. For example, if this column represents a height of a person, then this column represents different observation for a single variable. And in case of a row, it says one observation across multiple variables. So one observation means it will be the features of a single person or single object. So when you arrange them in the form of a matrix, you are dealing with linear algebra. So whatever data set we have, that might be, in most cases, it will be represented as a matrix. So you're dealing with linear algebra there. And in linear algebra, you should be familiar with what is a dot product, because linear algebra says dot product, element-wise multiplication, then you take the sum of the products. And basically, the dot product is a measure of similarity. Probably many of you might already know this thing. Dot product can be used to measure the similarity between two vectors. The larger the value, the more similar they are. So imagine if two vectors are 90 degree or perpendicular to each other, then the dot product will be 0. So there is no similarity between these two vectors. So dot product is actually a measure of similarity. And then I think you know about the linear combination of vectors. All these things will be covered detailed in the next 1.5 hours or 2 hours. And the linear combination of vectors represent how different features combine to form data points in machine learning. So you have many data points or many samples in that. And then these things can be thought of as a linear combination of vectors. So we will explain what is a linear combination of vectors. And then finally, when you have a huge data set with many hundreds of features or thousands of features, it'll be very difficult for the machine learning model to train on those data set and then build a model. So you need to find a way to reduce the dimensionality. You can reduce the number of features from say 100 to 10, then apply the machine learning algorithm, and then you get a better model. So for this, you need to understand about projections. You can project a vectors onto another. I mean, you can project a 3-dimensional, or you can reduce the number of dimensions of a data set from say 100 to 10 using projections. And basically that is what we are doing when you study about PCA, or principal component analysis. So how I plan to do the upcoming session is, we'll go through all the basics of linear algebra, including vectors, vector addition, vector linear combination, basis, all linear independence, everything we will go from beginning. And at the end, we will conclude with one of the applications, which is basically principal component analysis, and how these techniques are applied in principal component analysis. This is what I plan to do for the next few hours. So the first topic you should be knowing when you start linear algebra is about a field. Many terminologies will come again and again. It'll be better if you get a connection between all of these terminologies. So I'll be defining a field now, then a vector space and a subspace, then linear combination, then linear independence. All these things are connected. So it'll be good if you remember whatever things that we are discussing now till the end, because all these things are connected, and then only I think it'll make sense to understand what will be the connection between all these topics. So let's start. So what is a field? A field is simply a set of elements with 2 operations defined on that. So I can say 2 operations means normally you denote the operations as plus, which stands for addition, and multiplication, which is denoted by a dot. So the elements and these 2 operations are together known as a field. And this should satisfy the following 6 properties. And these properties are very common properties that we can say that additive closure. You take any 2 elements from the set, you add them, you should be getting another element, which is again in the same field F. Multiplicative closure means you multiply 2 elements, you take 2 elements from the field and then multiply them, you'll be getting another element which is also in F. And this field should have an additive identity 0, such that you should be getting A plus 0 equal to A. And there should be a multiplicative identity that is 1. And when you multiply A with 1, you will be getting A itself. There should also be an additive and multiplicative inverse in the field. So you take any element, there should be another element minus A, such that A plus minus A, you should get 0. Similarly, there should be a multiplicative inverse, But in case of multiplicative inverse, you don't need to take care of the 0. Take any element from the field except 0, you should be getting an inverse for that. Inverse means when you multiply a and its inverse, you should be getting 1. So these are the 6 properties that a field should satisfy. We'll see some examples for field. So suppose R is a set of real numbers with the 2 operations, addition and multiplication, plus and dot, normal number addition and multiplication. So to check whether this field R with addition and multiplication is a field, we'll be checking the 6 properties. And 2 of them are combined here. You know that R is closed under plus and addition, plus and dot. Because you take any 2 real numbers and then add them, you'll be getting another real number. You take 2 real numbers and multiply them, you'll be getting another real number. So R is closed under plus and dot. And there is an additive identity in the real numbers as 0. You take any number A, add it with 0, you'll be getting A itself. So there exists an additive identity 0, which is a member of R. There is also a multiplicative identity 1, which satisfies A dot 1 is equal to A. And for any element, you can find an additive inverse and multiplicative inverse, because A exists in R, so as minus A. Similarly, for any element A, there is an inverse. But for 0, there is no inverse because 1 by 0 is not there. So, but according to the definition, you don't need a multiplicative inverse for 0. So A inverse exists for all the real numbers. You just have to take 1 by A. So the conclusion is R plus and dot is a field. Okay. And to see an example which is not a field, you can take the set of integers z and the same operations, additions and multiplication. This satisfy 5 properties. The set of integers is closed under plus and dot, because you take any integers, you'll be getting an integer if you add them or multiply them. And the additive identity is also there. Multiplicative identity is also there. Additive inverse is also there, because for any element A in Z, minus A is also in Z. So additive inverse also exists. Regarding multiplicative inverse, that is a problem, because for you take, I think only for 1 there is multiplicative inverse. For all others, the multiplicative inverse does not belong to Z, because you take 2. And 2 inverse is 1 by 2, but 1 by 2 belongs to R but not belongs to Z. So you don't get a multiplicative inverse for all the elements in Z. So we can conclude that Z, the set of integers with the operations plus and dot, is not a field, because most integers do not have a multiplicative inverse in Z. So this is an example which is not a field. So the next definition is about vector space. So what is a vector space? So you define a vector space over a field. Okay, so let F be a field and V be a non-empty set whose elements are called vectors. Okay, we can say that V is a vector space if the following hold. So apart from the operations that we have defined for the field plus and addition, 2 operations are defined here, and they are known as vector addition and scalar multiplication. So vector addition means the symbol, you can represent it with plus itself, and it is a mapping from V cross V to V. That means you take 2 vectors, or you take 2 elements from V and then combine it, and then it will produce another element V itself. Scalar multiplication, you multiply a vector with a scalar, you will be getting another vector which is also in the same set V. So the axioms that should be satisfied by the vector space are following. You take 3 vectors u, v, w in the vector space V, and then two scalars alpha and beta in the field F, You can think of like what is the relationship between F and V is that you are forming V using the elements of F field. So, for example, I can say that a vector in 2 dimension, say vector in R2, 1, 2 is a vector, right? With x component as 1 and y component as 2, it is a vector. That 1 and 2, you are taking it from the field R or Z. So that's why we say that vector is defined over a field. As you take any 2 scalars from the field and you take 3 vectors from V, and it should satisfy the following properties. The first one is the commutativity, that is u plus v is equal to v plus u, and the associativity, I'll quickly go through this because all these things are very familiar to you. Associativity means u plus v plus w is equal to u plus v plus w. And there should be an additive identity. It's not about the other identity that we discussed previously. This is for vectors. So there should be a 0 vector in V such that u plus 0 vector should give you u itself. So this is a vector here. So you can say that we are overloading plus here. In the case of a field, this plus was adding 2 real numbers or 2 integers, but here we are using it to add 2 vectors. So we can say that it is some kind of operator overloading that we learn in programming. Okay. So, and there should be always an additive inverse for every vector. So you add a vector to minus u, then you will be getting the 0 vector. So again, I'm saying this is not 0, this is a 0 vector. We will come to the details of vector soon. Scalar identity means you can multiply any vector with 1, you should be getting the same vector. And finally, the 2 distributivity properties are there. Alpha, which is a scalar, and then you multiply it with u plus v, you should be getting alpha u plus alpha v. And distributivity can be also applied along through scalars. Alpha plus beta u is equal to alpha u plus beta u. So this is the properties that should be satisfied by a vector space. So to take some examples of vector spaces, the field F itself is a vector space because field is defined as a set of elements with 2 operations plus and dot. So that itself is a vector space. And then Rn, as mentioned here, Rn means a vector space which contains n elements. So, or else you can say that n tuples of real numbers from a vector space over R. This is a vector space because that we will prove soon. And then real m by n matrices that with the operations defined entry wise, that should be noted out, because you take any 2 m by n matrices, add them, you will be getting another m by n matrix. And then you take any m by n matrices and then do element wise multiplication, you will be getting another m by n matrix. And there is always an identity matrix. There is additive inverse, there is a multiplicative inverse. The commutativity holds for matrix addition, associativity holds. So all other properties are satisfied by this R m by n. And there are some special kind of matrices which are particularly important in machine learning, and those matrices are known as real symmetric matrices. And we will talk something more about this at the end of the session, real symmetric matrices. And these real symmetric matrices are also vector spaces. Okay. And then when you talk about vector space, there is something called vector subspace also. Vector subspace means a subset of vector space V, which itself is a vector space. Okay, so you take a subset of the vector space V, and you're taking only some of the elements from the vector space V, and then you check whether the smaller subset also satisfies all the properties of the vector space. Then we say the subset is a subspace. So some of the examples for subspaces are the vector space V itself is a subset, right? So it is a trivial subspace. And you just take 0 vector alone, that is a subspace, because imagine there is a vector space with just one vector, 0, and then that 0 vector satisfies all the properties of a vector space. So you can say that 0 vector alone is a subspace. And all the lines or planes through the origin are also subspace. I won't be going into the details of how we can say that these are all subspaces. Basically, what we have to do is take this and then check whether all the axioms are satisfied. And when you go through them, you can see that all the axioms are satisfied by this subspaces. So I'm just mentioning some of the examples of vector subspaces. Okay, now let's talk about what is vector. Vector is something, as you know, which has dimension, which has magnitude and direction. And R2 denotes a set of all vectors with two real numbers. So when we say R2, that means all vectors with two components. Okay, so in Euclidean space, you can represent a vector like this. You can represent a vector in R2, and you can also represent a vector in R3. But in all other higher dimensions, you'll be just writing a tuple of numbers. Okay, so in case of a 2D, in case of an R2, you can represent it in a plane like this. For example, this is a vector 3, 2. You take 3 on the x-axis and take 2 on the y-axis, and you'll be getting a vector, and that is this vector. I know you know these things, but still, I'll just mention what is this. What is vector addition and scalar multiplication? How do you add two vectors? This is how you will be adding. U and V are two vectors in Rn. That means these two are vectors with n components like this, and V is another vector in Rn. Then you add them. This is how the operation is defined. You do element-wise addition. And this is scalar multiplication. You take a real number k from the set R, then you multiply with the vector v, you'll be getting k v1 k v2. You multiply the scalar with every element in the vector. So these are the basic operations of vector, which are vector addition and scalar multiplication. There are other operations like dot product that we will come later. That is vector multiplication, but that is normally known as vector dot product or inner product. Now the most important topic of this vectors. So a linear combination of vectors. What is meant by linear combination of vectors? Suppose you have k vectors, which are all of them are Rn. So when I say Rn, you just need to understand that it has n components like this. N components will be there. So like that, you take k vectors, and one of them will be like this. Ui will be ui1, ui2, uin. So each vector will be having n components, and it's like that you have k vectors, u1, u2, etc. uk. And imagine there are k real numbers, alpha 1, alpha 2, etc., alpha k. And you can say that a linear combination of these vectors is just like this. V is equal to alpha 1 u1 plus alpha u2, alpha 2 u2 plus etc. plus alpha k uk. So basically what you're doing is you multiply every vector with the scalar and then finally add them all. So the resulting will also be a vector, because when you multiply a scalar with a vector, you'll be getting a vector. Okay, so you'll be getting k vectors here after multiplying every vector with the scalar. And when you add them together, you'll be getting a vector. So you'll be getting a new vector v. So this v is called a linear combination of these vectors. So this should be very clear, because you can imagine a data set like this. Every data point can be considered as a linear combination of the features of the data set. So that's how this relates to the machine learning. So we will come back to that later. So for example, to understand what is a linear combination, you take just two vectors. U, it is minus 5 2, and v is equal to 1 5. So this vector u is minus 5 2, and then v is 1 5. This small, I hope you can see my mouse pointer. I'm keeping on talking. So any response? Justin sir, I'm still audible, right?
Yes, sir, you're audible.
Okay.
And
Okay. So this u vector is minus 5 2 and this v is 1 5. So 2u plus 3v means you just scale this u. So this longer one will be 2u, and the 3v is this one. You're getting 3v, and then you just add them up. So 2u plus 3v. I hope you know how to add two vectors. So to add two vectors, you just need to complete this parallelogram. So you'll be getting this black vector here. So this black vector is actually minus 7 19. So we, in short, we can say that this vector minus 7 19 is actually a linear combination of minus 5 2 and 1 5. So you can think like this. If you have these two vectors, then you can combine them to get this vector. So basically, I can say these two vectors are enough. You don't need this vector because you take only these two vectors, and you can make this new vector, right? So in the data set, you can avoid some features like this because two features can derive, or if two features can linearly combine to form another feature, then you can avoid that feature, right? So that we will come later. So minus 7 19 is a linear combination of u and v. So we have seen what is a field and what is a vector space and what is a vector subspace, and then we have seen what is meant by a linear combination of vectors. And the next important definition is linear independent vectors. I think most of you know what is linear independent, but still a set of vectors is said to be linearly dependent if there exists scalars alpha 1, alpha 2, alpha k, not all zeros, such that alpha 1 u1 plus alpha 2 u2 plus etc plus alpha k uk equal to 0. So I know this definition seems a bit tricky, but this is very simple. You can say that I used to remember like this: a set of vectors is said to be linearly dependent if any of them can be formed by combining others. Okay, so you can think it like this. If I have a set of vectors, say I have a set of 5 vectors, and say one of them, maybe the fifth one, I can get it from the other 4 or other 3, or I can say the fifth one is a linear combination of first and second, then we can say that they are linearly dependent. So the set is linearly dependent. One of them is, I can say, redundant because it can be created using the other vectors. In the other way, if none of the vectors are linear combination of others, then we can say that they are linearly independent. Say, for example, you have 3 vectors, vector 1, vector 2, vector 3, and vector 1 is independent of vector 2, vector 2 is independent of vector 3, mean you cannot form any of these vectors by combining other 2. So then we can say that these set of vectors are linearly independent. So mathematically it is written like this: alpha 1 u1 plus alpha 2 u2 plus alpha 3 u3 plus etc plus alpha k uk equal to 0. And you try to find a solution for this one. You try to find alpha 1, alpha 2, etc alpha k. And if it has only trivial solution, that means if the solution is all zeros, definitely when you put alpha 1, alpha 2, etc alpha k all 0, this equation is satisfied. And if that is the only solution for this equation, then you can say that these vectors are linearly independent. If at least one of them is non-zero, then you can say that they are linearly dependent. I hope it makes sense. So to check whether the set of vectors is linearly independent, all that you need to do is to check this equation has solution, trivial solutions or non-trivial solution. There are many ways to find the solutions for this equation that that I didn't cover in this session. Gaussian elimination. You can reduce the set of equations to what we call augmented matrix, and then you can solve it, and then check whether it has a trivial or non-trivial solution. Okay. And regarding linearly independent vectors, a linearly independent set cannot include the 0 vector because see, suppose one of these vectors is a 0 vector, then that set of vectors will be definitely linearly dependent, because you can always find because see, 0 vector means you can put imagine this uk is a 0 vector, you can put any value here for alpha k, right? You can put 100, 10 or any value here because this will become 0. So all others will be 0. Alpha 1, alpha 2, alpha k minus 1 will be 0. This can be non-zero if this vector is 0. So in a set of vectors, if one of the vectors is a 0 vector, then that set is linearly dependent. And the other property is that any subset of linearly independent set is also linearly independent. You take any subset of linear independent set, that will also be linearly independent. That is, I think, that is intuitive, right? That is intuitive. Okay. This is what I said. Two vectors are linearly independent if neither is a scalar multiple of the other. So you take two vectors, and if one of the vectors is not a scalar multiple of the other, then you can say that these two vectors are linearly independent. Okay, so this is about a linearly independent set of vectors. Next definition is span of a set of vectors. So what is meant by span of a set of vectors? So to understand all these things, you should be still remembering what is a linear combination of vectors. So let again say k vectors are there, u1, u2, etc., uk. The span of this vector is denoted like this. Span of u1, u2, uk. This is a set of or linear combination of these vectors. So I think it like this. See, you have two vectors, say 1, 0 and 0, 1. Okay, these are the standard basis. Oh, sorry, what I can say, unit vectors in the R2. See, one standard basis. You can say standard basis 1, 0, 0, 1. What are the vectors that you can form with these two vectors by linearly combining them? And the set of all such vectors is called the span of those two vectors. I hope it makes sense. So take two vectors, you do all possible linear combinations on these two vectors, you'll be getting a pile of vectors, and that pile of vectors is called a span of that two vectors. Okay, so it'll be I think it is clear. Okay. And then what is meant by span of a linearly independent set? Previously I said you take any two vectors and then do any two or any n k vectors, and you do all possible linear combination, you'll be getting a lot of vectors, and that is called a span of such vectors. And imagine if these k vectors are linearly independent vectors, then that is called as the span of this is denoted like this, is a set of a linear combination. So this set has something something special about this, because a linearly independent set means these vectors are nowhere related to each other, you can say like that. And then you take the span of all these things, you will be getting a fresh complete set of vectors that can be represented using this k vector. So span of a set of vectors, span of linearly independent set, both are same, but we are putting an extra condition that these vectors are linearly independent. So from these two definitions, we are coming to the basis of a vector space. So what is meant by basis? Basis is again a set of vectors v1 to vn. This should satisfy the following conditions. So we say that a set of vectors B containing n vectors is a basis for the vector space V. I hope it's clear. You think of V as a vector space, and I'm taking some of the vectors from this V, say n vectors from this V, and I'm labeling it as B. Okay, a set of vectors. So this is a huge vector set which contains all the vectors, and this is a smaller one which contains some of the vectors from this V. And we say that this set of vectors is a basis for V if it satisfies the following conditions. The first one is the linear independence. The first condition is all the vectors in this B should be linearly independent. And the second one is the most important one. It should have the spanning property. What I mean by that is that you take the span of this vectors, that should be V. Okay, so that means that every vector in this V, the bigger V, can be created by linearly combining all the vectors in this basis B. So you can represent, you take any vector in V, you can get a linear combination of these vectors to get this V. So that is what mentioned here. You take any vector small v in this vector space, that can be uniquely written as small v is equal to beta 1 v1 plus beta 2 v2 plus etc plus beta n vn. So you linearly combine these n vectors and you will be getting any vector in V. So a basis, you can say basis as a minimal spanning linearly independent set. So the conditions are they should be linearly independent and they should span the entire vector space. And we can say that that V B is a what basis for V. Intuitively, I can say it like this. Suppose we have say 60 students in the classroom. We can think of the 60 students as 60 uh, vectors. Okay, and that is our vector space. Vector space contains 60 students. And imagine you take 3 students from the classroom and think like this. These 3 students can combine or work together in such a way that they can represent any student in the classroom. Okay, these 3 students can do whatever the other students in the classroom say I take 1 2 3, and if they work together in a particular combination, they will become student number 48. If they work in a different combination, they will become student number 49. Imagine like that. Then we can say that these 3 students is a basis for the entire classroom, or we can say that these 3 students are enough to represent the entire classroom. I hope it makes sense. Okay. Okay, and then the final definition of a dimension of a vector space. So dimension of a vector space means how many elements are there in the basis of a vector space. That is basically we call a dimension of a vector space. So in case of R2, I've already mentioned you what is R2. R2 is a vector with the 2 components, or you can think of like 1 2 2 3. Those kind of vectors are R2. So the dimension of this vector space is 2, not because it has 2 elements in it, because this R2 can be represented by 2 vectors in the basis. So vector space can have many bases, but one of the standard bases is 1 0 0 1. These two are 2 vectors, right? 1 0 and 0 1. You just need these 2 vectors to create any vector in R2. So we say that basis for R2 is one of the bases. There are many other bases also, but one of the bases is 1 0 0 1, because you can combine them, linearly combine them to get any vector in the R2. So we say that the dimension of R2 is 2 because the basis has 2 elements in it. Okay, this is what I mentioned. A vector space Rn has infinitely many possible bases. A vector space can have many possible bases. However, every basis of Rn contains exactly n vectors. So even though R2 has many bases, see some of the bases are written here. R2 1001 is a basis for R2. 111 minus 1 is a basis for R2. 2314 is a basis for R2. How this is found, I'm not covering it here, because you take any vector in R2, you can get it from these 2 vectors, combining them. So all these are bases for R2, but one thing is guaranteed is that you cannot reduce it further, because there is no single vector which can represent the entire R2. So you need at least 2 elements in the basis to represent the R2. So we say that the dimension of R2 is 2. Or in general, dimension of Rn is always n, because the basis has n elements in it. So far we have seen, I'll just do a recap, because, as I mentioned already, you need to get a connection because all the definitions are connected to the other. It's like a chain. So we've seen what is a field, what is a vector space, what is a vector subspace, and then what is meant by linear combination of vectors, and what is a linear independence, and then Then we have seen what basis of a span of a vector set of vectors, and then we have seen what is basis. Okay, and then the properties of basis. And now we are getting into linear transformation. So transformation is a mapping from one vector space to another, T. It is denoted as T. It is a what we can say, it is a mapping from one vector space V to another vector space W, such that you take any two vectors U and V in the small v, and is scalar C. Transformation of U plus V is equal to transformation of U plus transformation of V, and transformation of CU is equal to C into TU. So any transformation, we will see what is transformation soon. An example is there, but any transformation that satisfy these two properties is called a linear transformation. Transformations basically, you can think it like a function. A function basically maps one element in a set to another element, right? But in the case of transformation, that element is a vector. That's the only difference. That you take a vector in one vector space, apply some function or some mapping, then you get a vector in another vector space. Then that is called a transformation. So a linear transformation preserves. So this two properties actually mean this thing. A linear transformation preserves both vector addition and scalar multiplication. So this is vector addition. That is, you add two vectors in the vector space V, apply the transformation, you're getting a new vector, right? And you can do you'll be getting the same thing if you apply the transformation for the first vector, apply the transformation for the second vector, and then add them. So these two will be same. That's what mentioned here. The linear transformation preserves vector addition and scalar multiplication. So any transformation that satisfies these two properties is called a linear transformation. So now how we do this transformation? So normally a transformation is represented by a transformation matrix. A transformation matrix represents a linear transformation using matrix multiplication. So imagine this is matrix A, 2 by 2 matrix, and this is a vector in R2, x1, x2. So you multiply A into X. So this is a 2 by 2 matrix, and this is a 2 by 1 vector. So you'll be getting a 2 by 1 vector again. 2 by 2 into 2 by 1, you'll be getting a 2 by 1. That is another vector in R2. So I can say that B is equal to AX. In this one, matrix multiplication, you'll be getting a new vector B1, B2. So this matrix, which transforms a vector x1, vector x to another vector b1, b2. This is a linear transformation. You can check how you can make sure that this is a linear transformation. You apply this to x and y, check whether the addition is preserved. You apply scalar multiplication, check whether the scale multiplication is preserved. Then you can say that this is a linear transformation. So so this matrix A actually encodes the linear transformation. So whenever we say about linear transformation, we are talking about a transformation matrix that do this linear transformation. So so there are some common transformations that we use in machine learning. One of them is the identity transformation. So identity transformation is just, it keeps everything unchanged. So T of X is equal to X. This is identity transformation, right? So you take a vector in a vector space, apply the transformation, you're getting the same. So then that is called identity transformation. So this transformation can be represented using this matrix 1, 0, 0, 1. You can verify that this is correct, because for any vector x is equal to x1, x2, apply this ix 1, 0, 0, 1, x1, x2, multiply, you'll be getting x1, x2. So you're taking x1, x2, applying the transformation, getting x1, x2. So this is what identity transformation. So the transformation matrix for identity transformation is this one. And the other, I'll say two more transformation. And the other one is reflection transformation. Reflection can be along the x-axis or along the y-axis. You take a vector in R2 and apply this transformation. See, this is the transformation matrix for reflection along x-axis. So 1 0 0 minus 1. This is the matrix. Multiply it with a vector x. We'll take an example. So this is imagine x is 3 2. I think I didn't, yeah. Okay. 3 2 is a vector. I'm leaving it to your imagination. You imagine a 3 2 vector here, okay, and then I'm reflecting it along x-axis. So if this is the 3 2 vector, if I'm reflecting it along the y-axis, you should be getting a reflection on the bottom side, right? So it should be 3 minus 2, right? This one. So that is what you are getting when you multiply this vector with this transformation matrix. So you multiply 1 0 0 minus 1 into 3 2. That will give you 3 minus 2. So that is the reflection of the first vector 3 2, 3 minus 2 along the x-axis. To get it along the y-axis, you have to do the other way. Okay. And the other common transformation is rotation transformation. So rotation transformation is this one. The transformation matrix is cos theta minus sin theta, cos theta. So this causes a rotation in the anti-clockwise direction. So theta is the angle by which you want to transform the vector. So I've shown it in the figure. This is the vector x, and suppose you want to rotate this. This is, I hope you can see the grid lines here. This is 2 1 2 1. So this vector is 2 1. And if you want to rotate it by 90 degree, you form the transformation matrix, that is cos 90 minus sin 90, sin 90, cos 90. So that is 0 minus 1 1 0. Okay, cos 90 is 0, minus sin 90 is 1 minus 1, and then sin 90 is 1, and cos 90 is 0. And multiply this with the 2 1. The answer is minus 1 2. So I've drawn it here, minus 1 2. This is the red vector is the transformation. So you can see visually here that this vector has been rotated by 90 degree by this transformation matrix. Okay, so this is the rotation transformation. So these are some of the common linear transformations. Now some terminologies are there. A transformation T from Rn to Rm is a rule that assigns each vector x in Rn to a vector in Rm. So basically what that does, the transformation does is this one. It takes a vector in Rn and then transform it to another vector in another vector space. Say it may be in Rn or it may be in some other vector space Rn. And like in case of a function, we have some terminologies like domain, codomain, range. Those kinds of definitions are familiar for you, but in same thing exists in this linear transformation also. So if T is a transformation from Rn to Rm, then Rn is called a domain of the transformation T, and Rm is called the codomain of the transformation T. Okay, so you take any vector x in Rn and apply the transformation, then we will be getting a vector in Rm. So we will say that the new vector is the image of this x. So T of x or B is the image of x. That is the terminology for that mapping. And the set of all images. So you take the transformation on all the elements of Rn. You'll be getting vectors in Rm. So the set of all such vectors is called the range of transformation. Okay, so domain is something different from range. Domain, codomain, sorry. Codomain means the entire Rm. Range means the subset of this codomain. It may or may not be same as this Rm. If it maps to only some of the vectors in Rm, then that is the range of this transformation. So domain, codomain, image, and range are the definitions of this. And next. So 4:30. Okay. Next is column space of a matrix. What is meant by column space of a matrix? So matrix, you can think matrix has many columns, right? So if you think of each column as a vector, and then what is the column space of a matrix A, denoted as column, is a set of all vectors that can be expressed as a linear combinations of columns of A. So you have a 3x3 matrix, then you have 3 columns. You take each column as a vector, apply linear combinations, all possible linear combinations on these 3 columns. So you're getting a set of vectors, and that set of vectors is called column space of this matrix A. So if T is a linear transformation associated with the matrix A, then the column space is same as the range of A, range of the transformation. I think that makes sense, because the transformation, what I meant by range of a transformation is the set of all elements in the codomain which gets mapped from the domain. So that is a range. So if you represent the transformation T as a matrix, transformation matrix, and then the columns of that A, if you treat it like a set of vectors, then the linear combinations of these all such columns form the range. So what I mean to say is that column space of this matrix A is same as the range of the transformation T, provided this matrix is the transformation matrix corresponding to this transformation. So I believe that is fine, because you can think T and A. I can say that I can say this transformation basically rotates this vector by some particular angle, right? And that transformation is encoded in this matrix A. So that is the relation between transformation and the matrix, transformation matrix. So T and A are the same. But when you say about transformation, you say that the range of the transformation. But when you talk about the corresponding matrix, you say that is the column space of this, the transformation or the transformation matrix. And the next definition is kernel of a transformation. So kernel means you take a transformation Rn to Rm. Kernel of T is a set of all vectors in Rn that maps to the zero vector in Rm. So Rm has a zero vector. Okay. So who all from Rn gets mapped to zero. Set of all such vectors in Rn are called kernel of the transformation. So it is the other way. In case of a range, we say that these all the elements in Rm who has a pair in Rm, or I can say that some of the you take all the elements in Rm which gets mapped to some of the elements in Rm. It need not be all of them. Maybe say all the elements in Rn gets mapped to 10 elements in Rm. Then we say that those 10 elements are the range of this transformation. But when you talk about kernel, it is the other way. You take the zero in Rm and see who all gets mapped to zero, and that is the kernel of this transformation. So mathematically, you can write it like this: kernel of transformation is equal to x in Rn, such that t of x is equal to 0. And like we mentioned for the range and what was that, range and column space, similar thing exists here. Kernel and null space are same. Null space of the corresponding transformation matrix is the kernel of transformation. So these two are basically same. Null space of the transformation matrix and kernel of the transformation. So you should always remember that these two are same. A and T are same. T is the transformation, A is the corresponding transformation matrix. So when you say about transformation, you say kernel, and while mentioning about matrix, you just say null space of matrix. Okay. Now, why do we study all this thing, linear transformation and basis? So basis, I think you remember the definition of basis. I made an analogy about basis about the students in a classroom. I hope you remember. So the set of vectors which can represent the entire vector space, or which can span the entire vector space, is called a basis, right? So now we will combine these two, linear transformation on a basis. So take a transformation T, Rn to Rm, be a linear transformation. Every vector x in Rn can be written using the standard basis E1, E2, En. So standard basis means for R2 the standard basis is 1, 0 and 0, 1. For R3 the standard basis is 1, 0, 0, 0, 1, 0 and 0, 0, 1. Okay, so these three vectors are enough to represent any vector in R3. Okay, so if we have the standard basis for a vector space, and you apply this transformation on this standard basis, and you getting this one. So t so you take any vector t of x which is represented like this, apply the transformation. Since t is linear, we already defined what is linear transformation. So since t is linear, you can write it like this: x1 into t of e1, x2 into t of e2, plus etc. plus xn into t of en. So to know a linear transformation t, it is enough to know that what it does to the basis vector. So what all you need to know is understand what the transformation does to the basis. So if you know what this t of e1, t of e2, then you can represent it the entire vector space. The transformation, how the transformation will affect the entire vector space, can be understood by checking how the transformation affect the basis alone. Okay, so and to get a transformation matrix, all you needed to get is apply the transformation on the basis and then put them as okay. Apply the transformation on the standard basis, and then you put them as a column of matrix, and you will be getting a transformation matrix. Okay, so we have reached what checkpoint here. You have any queries up to now? Okay, so we'll continue. Next topic that we are going to discuss is eigenvalues and eigenvectors. Eigenvalues and eigenvectors, I think I'll do the example first and then go to the definition. Actually, we are still in the linear transformation section. So we are still dealing with linear transformation and then eigenvalues. We all know how, we all heard about eigenvalues and eigenvectors. We all know how to calculate eigenvalues and eigenvector. And so I won't get into the details of calculating the eigenvalues and eigenvectors. What I'll do, what is the meaning of eigenvalues and eigenvectors? That's what we need now, because the mathematical calculation and all those things, I think already you matrix. I can say that this is a transformation matrix. Imagine this is a transformation matrix. Transformation matrix, by transformation matrix, what I mean is you take any vector and then multiply this matrix with that vector, you'll be getting a new vector, right? So that vector will be transformed to a new vector. So there are some special vectors called eigenvectors, which has a property that when you multiply this matrix with that vector, the transformation is just scaling of that vector. By transformation, we already know transformation can be anything. So this vector can be rotated this way, this way, this way, or flipped this way. It can go any. After transformation, this small blue vector, there is a blue vector here. This vector can go in any direction, right? After a transformation, when you multiply this vector with a matrix, it can go in any direction. But imagine there is a vector, say this vector 1 1. In this example, this is 1 1, and you apply this transformation 3 1 1 3. The change to that vector is only this one. This vector is transformed into this longer one. This is 4 times this vector. 1 2 3 4, 4 times this vector. So we will say that this vector 1 1 is an eigenvector for this transformation matrix, because the transformation is just a scalar multiple of this original vector. By scalar multiple, what I meant is it can go in any direction, in this way or in the opposite direction. It can be negative also, but not in this way. And what is eigenvalue is, see, you take this 1 1, after the transformation this becomes 4 4. So the 1 1 became 4 4. So it is 4 times the original vector. So the corresponding eigenvalue is 4. That's what eigenvalue and eigenvector. So again, I'm defining it in the other way. Normally we will say we will study how to calculate eigenvalue and then how to calculate eigenvector. I'm doing it in the reverse way because I'm saying what is eigenvalue. I won't tell anything about how to calculate eigenvalue and eigenvector. It involves characteristic equation and then finding the eigenvector after you get eigenvalue. So that things I won't cover, because for this matrix, using the mathematical methods, you found that the eigenvalues are 4 and 2. Okay, imagine you somehow you found this one 4 and 2, and you take this 4 eigenvalue, the corresponding eigenvector you got is 1 1. So that means 1 1 is an eigenvector for this transformation matrix, and the corresponding eigenvalue is 4. But I believe what you understand is what is the meaning of all these things. This means that this 1 1 can only be transformed in such a way that it gets scaled by this transformation matrix. Using this transformation matrix, you can only scale this vector. So we call this as eigenvector, and how much you scale it, that is given by this eigenvalue 4. So actually, this is not the only eigenvector. Any scalar multiple of this 1 1 will be an eigenvector. You take 2 2, this vector 2 2, apply this matrix, you will be getting 8 8. So any scalar multiple of this 1 1 will be an eigenvector, and corresponding eigenvalue will be 4. Similarly, for the lambda 2 is equal to 2, the eigenvector is 1 minus 1. 1 minus 1 is a vector somewhere here. You take this vector, apply the transformation, you will be only getting a new vector in the direction of this new, in this 1 minus 1. So that's what is special about eigenvector. It is a vector whose direction does not get changed after a transformation. Okay, and how much is that scaling that is given by eigenvalue. So now we get back to this definition of eigenvalue. So suppose there is a transformation from V to V, a linear transformation, and let A be the matrix representation of this transformation T with respect to some basis of V. A non-zero vector U in V is an eigenvector of T if there exists a scalar K in R such that transformation of U, you apply some transformation to this vector, you will always get a scalar multiple of this U, Ku. Or in other words, this is the same as AU is equal to KU, because transformation can be represented as a matrix, transformation matrix. So AU is equal to KU. So the scalar K is called eigenvalue associated with the eigenvector. So hope that makes sense to you. Okay. So eigenvalue, eigenvector, what is the geometric meaning of this thing? Again, I'm saying I didn't mention how to calculate eigenvalue and eigenvector. I hope you can refresh that. Now, this one, let be a linear T be a linear transformation on a vector space V. There is a term called invariant subspace of transformation T. It's a set of vectors U such that transformation of U is lambda U. Okay, that means subspace of what all the vectors that you can get by using this transformation is called invariant subspace of this U. I think I can make it clear, because in this direction, this is a vector space, right? So this vector, this is called invariant subspace because it does not change direction. So that is why it is called invariant subspace. So all the vectors along this direction forms a vector space, and that vector space is called an invariant subspace. Okay, now what is so? Why do we do this eigenvalue and eigen vectors? So now I think we are slowly moving into applications of whatever we have learned so far, and we are getting into the details of how we can apply some of these things, not all, but some of these things into our metrics. So what is the relationship of metrics and machine learning? That we have a data set which can be treated as a matrix. So we need to understand what is a diagonalizable matrix. A square matrix A is diagonalizable if there exists an invertible matrix P such that P inverse A P is equal to D. So a diagonal matrix is a matrix which has elements or non-zero elements along the principal diagonal only, and all the other elements will be zero. That you all know. Diagonal matrix will have elements only on the diagonal, principal diagonal. Okay. And what is so special about diagonal elements is that suppose I can decompose a matrix like this. Suppose I have a matrix A, and I want to find the power of this matrix A raised to k. You know how difficult it is to multiply a matrix with itself. A square you can find out. After that you need to multiply it with again a. So to do A raised to 10, you need to do 10 matrix multiplications, right? So it is not so easy to do 10 multiplications. And imagine if it is 100, it becomes very huge, right? 100 multiplication, 100 matrix multiplication. Okay. So suppose you have a method using which you can decompose this matrix or factorize this matrix in this way: P, D, P inverse. I'll get into what are this P and P inverse and all. But imagine like we do factorization for numbers. See, I can represent number 12 as 3 into 4, right? So similarly, I can represent a matrix as a product of three other matrices, P, D, P inverse. Okay, so why do we do this? Why do I have to decompose this into this format? So when you decompose this vector, and if you can decompose it in such a way that this middle matrix D is a diagonal matrix. Imagine there is some way to do this decomposition that we will talk about now. But suppose somehow you decompose this vector matrix A into P, D, P inverse. P is an invertible matrix, and so we'll say what is P and what is D and all everything we'll say. But imagine you have done this thing, and D is a diagonal matrix. Okay. And then computing the power becomes simple. See how it becomes like that. A square. What is A square? A square means P, D, P inverse into P, D, P inverse. So you can join these together: P, D, P inverse P, D, P inverse. So you do the calculation. P inverse P is I, and D, so I get cancelled. So P, D square P inverse. So A was this one, P, D, P inverse. A square is P, D square P inverse. And you do one more thing, A cube. A cube is A square into A. So this is A square. That is P, D square P inverse into A. This is A. Again, you do the multiplication. P inverse P, this part gets cancelled because this becomes I. So P, D square into D. P, D cube P inverse. So in general, you can write that A raised to K, let the power be anything, any huge number. Then this A raised to K is simply P, D raised to K, P inverse. Okay. So think like this. If K is 100, and if you're doing A raised to 100, you have to do 100 matrix multiplication. Now, here what is so special? Here also there is a matrix D raised to K. But D raised to 100 is very easy to calculate because D is a diagonal matrix, and you know that diagonal matrix can be multiplied very easily because you have elements only on the diagonal elements, right? So when you say D square, you just square the numbers along the diagonal elements. When you say D raised to 100, you just take the 100th power of every element in the diagonal element. All others remain 0. So taking the power of a diagonal matrix is very, very easy compared to taking the power of a normal matrix. Okay. So this does not involve any matrix multiplication. You just do normal integer or say number multiplication, and then you multiply it with the two normal matrices. So you can see only 3 matrix multiplications here: P into this one matrix multiplication, and take that into multiply that with the P inverse. So you have only 3 matrix multiplication instead of 100 matrix multiplication. I know that this is 100 multiplication, but this multiplication is very easy because you just need to take the power of all the diagonal elements. Okay. So powers of diagonal matrix are easy. You simply raise each diagonal entry to this one. So now the question, how we can decompose this into P, D, P inverse? Where do this P, D, P inverse comes from? So that's what I'm mentioning here. A square matrix is you cannot diagonalize every matrix, so that you should understand first. A square matrix A is diagonalizable if there is there exists an invertible matrix P such that P inverse A P equal to D. So what you have to do is the diagonal entries of D are eigenvalues of A. The columns of P are corresponding eigenvectors. So that is the clue, and the proof of this and all is beyond the scope of this session. But I can say that D, given a matrix, what you have to do, whether you how do you check whether it can be diagonalized, whether you can decompose this into PD P inverse. What you have to do is, if it is an n by n matrix, check whether it has n distinct eigenvalues. So as I already told, I am not mentioning about how this eigenvalues can be calculated, but imagine you have n distinct eigenvalues, and then A is diagonalizable. So if A is an n by n matrix, and if you are able to find n distinct eigenvalues for them, I think you know that not all n by n matrices will have n eigenvalues, distinct eigenvalues. Some of them will be same. But you think it like this: suppose there is a matrix which has n distinct eigenvalues for n by n matrix. In that case, it is given, or it is proven that the columns of P are linearly independent eigenvectors of A. Okay, you can in another way you can decompose matrix diagonal. You can diagonalize a matrix only if it has n distinct eigenvalues. In this case, the columns of P are linearly independent eigenvectors of A, and D contains the corresponding eigenvalues along its diagonal. So I'll conclude like this. See, you take a matrix A, say it is 3 by 3 matrix, find the eigenvalues, and you obtained 3 distinct eigenvalues. Then there is a theorem that it says that if you have 3 distinct eigenvalues, and the corresponding eigenvectors will be linearly independent. This is a theorem that we are not going to prove now. But the eigenvalues corresponding to eigenvectors corresponding to distinct eigenvalues will be linearly independent. Okay. So what you have to do is you find the 3 eigenvalues, find the corresponding eigenvectors, and put them as a column. Then that is P. Okay, you put them put the eigenvectors as columns of the matrix P. Then you will be getting eigen P. And how to get D? D is just put the eigenvalues along the diagonal. So that is D. How to get P inverse? That you have to find. P inverse you have to find. Because still that's okay, because finding inverse is somewhat difficult, but still you have to find only once rather than finding a raised to 100. This is better. Okay, so this is called eigen decomposition. So that's one of the applications of. So where does this apply in ML? You can say if you can decompose a data set like this, it makes computation faster. Okay, so now we are getting into the last portion of the session. We need to mention about what is orthogonality and orthogonal projection and all. So I'll quickly skim through all these topics since we are getting closer to the end. Okay. So now we will define what is a dot product of two vectors. So this is I think you all know this thing. What is dot product? Dot product is defined as you do element-wise multiplication and then sum x1 y1 plus x2 y2 plus x etc plus x and yn. So in matrix notation, this can be x dot y is same as x transpose y, because you just transpose this thing and then you matrix multiply them, you will be getting same thing. So x dot y is same as x transpose y. And as I already mentioned in the first slide, dot product measures the extent to which two vectors points in the same direction. So if the dot product is very high, that means they are very similar. If it is 0, then they are perpendicular to each other, then they are dissimilar. So that is how we can use dot product to measure how similar two vectors are. And the next definition is what is meant by length of a vector. Length of a vector, or it is also known as magnitude of a vector, or it is also known as a norm of a vector. That is square root of the square sum of the squares of the components. So square root of x1 square plus x2 square plus etc. plus xn square. This is same as square root of x transpose x. So basically you do dot product of a vector with itself and then take square root. So that is the length of a vector. Same, these two are same. You can check this thing. X1 square plus x2 square plus this is same as x transpose x. Okay, so that is dot product and this is the length of a vector. And one more final thing, how do we find the angle between two vectors? The angle between two vectors is given by this equation. Phi is equal to cos inverse x transpose y, x dot y divided by length of x into length of y. So all the mathematical derivations are shown here. I'm not getting into the details of this thing. So this is the angle between the vectors u and v, and that is given by this equation. You take the dot product between the two vectors, find the length of the vectors, divide the dot product with the product of length, and then take the cos inverse. So when the angle is 0 degree, that means that the vectors are in the same direction. When the angle is 90 degree, the vectors are perpendicular. Okay, so if you're getting dot product as 1, then that means they are perpendicular to each other. Okay, so that's what we are getting into, the orthogonality. So what is meant by orthogonal vectors? Orthogonal vectors means two vectors are said to be orthogonal or perpendicular if their dot product is 0. X dot y, I think I mentioned this as 1 before. Okay, x dot y is equal to 0, and we write it as x perpendicular y. In addition to this, if the length of these two vectors are 1, then we will call them as orthonormal. That is, length of x and length of y is equal to 1. Then we will say that orthonormal. So this is the case of two vectors. We say that two vectors are orthogonal to each other if their angle between them is 90 degree, or in other words, x dot y is equal to 0. And if the length of both vectors are 1, then we will say that these two vectors are orthonormal. Now you take a set of vectors, set of vectors v1, v2, etc., vn, and you can say that they are orthonormal. With this definition, you take any two vectors in the set vi and vj, do a dot product, and it will be 1 if I not equal to j. It will be 0 if I equal to j. It will be 0 if I not equal to j. So what this means is I equal to j means vi dot vi, right? So vi dot vi is actually it gives you the length, right? As I already mentioned, length means this one. Take the dot product of vector with itself and take the square root. So that is a length. So when I say vi dot vi, that means length of the vector vi and square root, that is 1. So that means that every vector should have length 1. That is this part mean. And when you take two vectors which are different, that is I not equal to j, then their dot product should be 0. That means they are orthogonal to each other. So this is written in a mathematical way like this, or another way I can say that a set of vectors is said to be orthonormal if the length of all the vectors in the set is 1, and you take any two vectors in the set, the angle between them should be 90 degree. Okay, so that is orthonormal vectors. And what is so special about orthogonal vectors is that a set of orthonormal vectors is linearly independent. Okay, so that proof again I'm leaving. Set of orthonormal vectors are linearly independent. And one more point, 0 vector is orthogonal to every vector, because you take dot product of 0 vector with any vector, you'll be getting 0. So if the dot product of two vectors is 0, then that means they are orthogonal. So we can conclude that 0 vector is orthogonal to every vector. And now again we are going back to the basis. So consider a vector space V and a basis b1, b2, etc. bn. And we say that if these n vectors are orthonormal, that means you take any two vectors in this basis, and if they are 90 degrees to each other, then we say that these vectors are orthonormal basis. So what is so special about orthonormal basis is that when you have a basis which is orthonormal, like this b1, b2, we'll call this as ONB, or orthonormal basis. then every vector in Rn can be written as like this. So I know this, yeah, I'm getting late. So you take any vector v, you can represent it as a linear combination of this b1, b2, etc., bn, like this. The equation is this one. I am leaving the derivation v dot b1 into b1 plus v dot b2. It's very easy to calculate because you this is a vector for which you want the linear combination. What you have to do is take this vector, dot product it with b1, and then multiply it with v1. So you'll be getting a scalar here, multiply it with v1, again a scalar, multiply it with v2. So it is easy to calculate the linear combination if the basis is a orthonormal basis. Okay, so that is the property of orthonormal basis. And the next definition we will see is that orthogonal matrix. Orthogonal matrix, we have a matrix, and if the columns of the matrix are orthonormal, then we will say that the matrix is orthogonal. So this matrix has a I mean, you take a matrix and consider the columns of the matrix as vectors, and you take any two columns and find that they are orthonormal to each other, then we say the matrix itself as orthogonal matrix. And this orthogonal matrix has a property that A transpose is equal to I, which is equal to A transpose A. So this is very, very, very important, because you know that finding the inverse of a matrix is not very easy calculation. But now, if you have an orthogonal matrix, then finding the inverse is very easy, because the inverse is just a transpose of the matrix A. So the proof is not given. So so in machine learning, if you have a matrix which is orthogonal, then it is very easy to find the inverse, because you just need to transpose the matrix. Transpose is easy to find, right? So we have some orthogonal matrices in machine learning, so that you will understand. And then you can apply this rule, that is A transpose is the A inverse for an orthogonal matrix. And this orthogonal matrix has some other properties also. Transformation by orthogonal matrix do not change the length of a vector. If you have an orthogonal matrix and you use it as a transformation matrix, then a vector will be changed, right? Then you'll be getting a new vector. But one thing is guaranteed, that the length of the vector will not be changed by an orthogonal matrix. Also, you take two vectors, and there will be an angle between those two vectors, right? And you apply this transformation by an orthogonal matrix to these two vectors, you'll be getting two new vectors. But the angle between them will be preserved. So these two are some of the properties of orthogonal matrix. And the next is orthogonal projection. So projection is, I can simply say that this is the vector v in a particular direction. So I want to know how much information this v is captured in the direction of u. So you just need to find the shadow of this v on u. So this is what we call, this ku is called the projection of v onto u. So this concept is used in the principal component analysis or dimensionality reduction technique. So now this vector is v is in 2 dimension, right? So if I project this into this line, this becomes a 1 dimension, right? So you can reduce the dimension of this vector into 1, because this becomes a 1 dimensional vector. So this can be applied to any dimensions. So you can project a vector into a lower dimension. Definitely you will be losing some small amount of information, but PCA ensures that you capture the most important values and make sure that your data remains as good as possible. I mean, you will be reducing some kind of information. If you are reducing the number of columns in a data set from 100 to 50, definitely you are going to lose some information, right? But PCA will ensure that you are not losing that much, and you are avoiding only the information that are redundant. So the concept of projection, orthogonal projection, is used there. So this is the equation for projection that I'll skip now, and I'll stop with this PCA. So what is PCA? Principal component analysis is a linear transformation. It finds a direction in the data with maximum variance. So we'll be creating new features. So PCA is a feature extraction technique. So suppose you have 10 features, and from these 10 features, I'll be extracting say 5 features, which will still have the information contained in the 10 features. So for that we need eigenvalues, eigenvectors, everything comes here. I think I can't get into more details now, but we whatever we are applying here is the orthogonality is applied here. How do we find the linear combination of this original features? All these things will be applied in PCA. So how PCA is applied in machine learning? It reduces dimensionality because it keeps important information while using fewer feature. Okay, you can remove some of the unnecessary informations by reducing the number of features, and it removes noise because some small way. See, some of the features will not have much variance, right? So those informations give you. Suppose there is a column which is same for all elements for all examples, then that column doesn't give you any information at all, so you can remove that. So that thing will be taken care by PCA. Eliminate redundancy. So if there are two features, suppose there is a column called age and there is something which is very close to age, and then you need to keep only one of them, right? So there'll be a new feature extracted from these two, and PCA will make sure that you are avoiding or you are removing unnecessary features. And definitely when you're reducing features, that means you are speeding up training, right? And also by reducing the number of features, you can visualize your data better. Suppose you have a 10 features and you are able to reduce it to 10 features, 2 features using PCA, then you can plot it and see how your data looks like in 2D. And also it prevents overfitting by discarding irrelevant variation. So it simplifies the data while preserving the structure. That's what PCA does. And this is how the PCA is done. For applying PCA, first you need to find the covariance matrix that we can't get in. Covariance matrix, I can say that how two features are related, that is given in the covariance matrix. For example, I can say that height and weight are somehow related, right? So they have a positive correlation, right? I mean, if the height increases, normally weight should also increase. So, and some will have the opposite relation. See, covariance will be negative if you study more. You can think of something like when you do more, the result is getting lower. That kind of features will have a negative covariance, and some features will have. You take two features. If one feature does not have any influence on the other, then the covariance will be 0. So there will be positive value means two features are going the same direction. Negative covariance means one increases, the other one decreases. Zero covariance means that means they have no relations at all. So there is a matrix which you can form using the features of the data set, and that matrix is a symmetric matrix. That's what I said. Symmetric matrix is there. So that metric covariance matrix will give you the relationship between features, and that matrix will be a symmetric matrix. And symmetric matrix has some features like A transpose is A, and for a symmetric matrix, all eigenvalues are real, and eigenvectors for distinct eigenvalues are orthogonal. So definitely you can you can apply the decomposition P inverse that we have already discussed. And since this is orthogonal, P inverse can be replaced with the P transpose. Okay, so we can decompose this A into P transpose, and you can find the eigenvalues and eigenvectors for this thing. And what this PCA does is you can take the or you find the compute covariance matrix, find the eigenvalues and eigenvector. You sort the eigenvalues with the largest first. So find the eigenvalue with the largest value, project the data onto the eigenvectors. Okay, you take the eigenvector corresponding to the highest eigenvalue, project your data onto that, and then how many dimensions you need, how many features you need, you take the top. Suppose you needed only 5 features out of 10 features, and you find the top 5 eigenvalues and their eigenvector, and project the data set onto that, and then you'll be getting only 5 features. So these eigenvectors represent the direction of maximum variance. So I think I stop here now because we are running out of time. Justin sir.
Participants, if you have any questions, you can ask. Thank you, Midin sir, for nice overview of basics of linear algebra for machine learning. Thank you, sir.
Okay. Thank you. Thank you.